All right, we're going to conclude section 15.6 in this video, and we're going to do an exercise on page 1046. We're going to do number 9. The directions say in exercises 5 through 9, use a parameterization and equation 4 or 5 to evaluate the surface integral over sigma of f dot n ds. So equations 4 and 5 are just the basic equations that I gave at the beginning of this section as to how to evaluate a surface integral. So they're just saying they're two different notations for the same thing. All right, so for number 9, they give us our vector function f of x, y, z equals sine of x squared plus y squared, sine of x squared plus y squared is the first component. Second component is y times sine of x squared plus y squared. And the third component is just 0. All right, and then our surface sigma is composed of the part of the cylinder x squared plus y squared equals pi over 2. So between the planes z equals 0 and z equals 1, including both the bottom z equals 0 and the top z equals 1, n is directed outward from the cylinder. All right, so let's say S1, and let's deal with the easiest surfaces first. So the planes, which are z equals 0, and that is inside of the cylinder. So x squared plus y squared is less than or equal to pi over 2. X squared plus y squared is less than or equal to pi over 2. And then S2, so this is the bottom of the cylinder. Top of the cylinder was z equals 1. And that's also that top of that plane z equals 1, but inside the cylinder. So x squared plus y squared is less than or equal to pi over 2 there as well. And then lastly, the sides of the cylinder. So S3 or side of the cylinder, which was x squared plus y squared equals 2. X squared plus y squared, pi over 2, excuse me, not 2. And that is between z equals 0 and z equals 1. So these are our surfaces, but these are not our parameterizations for our surfaces, nor are they our bounds for our surfaces, or the bounds for the parameterizations. So this was with z between 0 and 1. All right, so what we'll have to do is we'll have to parameterize all three of these surfaces, take them and substitute them into our vector field, and then do find the partial derivatives of our parameterizations, take the cross product, and we're going to dot the vector field with the parameterization substituted in with the cross products, and then we evaluate our integral. So that's just an overview of the steps, but we'll go through each one of them in detail. All right, so let's start with S1 and parameterize that, and then we'll set up that integral. So for S1, let's do this. The surface integral over S1 of, I'm sorry, not G, F dot N ds. That's what we need to do. So now that means we need to parameterize this surface. So my go-to things I'm going to see, can I use my favorite parameterization? If I can solve for x, y, and z and whatever I have there, x, y, or z, excuse me, then I'll use my favorite parameterization. They've already solved for z, so I'm going to use x equals x, y equals y, z equals f of x, y, and then what are my bounds for x and y? So because this region right here is a circular region, in all likelihood, I can do one of two things. I can switch to a cylindrical or polar parameterization in terms of x and y, or I can go ahead and set things up, see what my integrals are going to actually look like, and then see, do I even need to deal with that? So let's set up the integral. We'll sketch that region since we know we're going to end up evaluating a double integral. So we'll just do a little rough sketch of that region. So this is a circle centered at the origin with a radius square root of pi over 2. And that will be our region R1. It corresponds to S1. It's also going to be a region for R2 as well, since they have the same region. So, and if you wanted to know what this figure looks like, you can just look at figure 15.39D on the same page. So the cylinder, this is kind of what our region, our surface looks like, with the exception of it's shorter and has a different radius than that cylinder has. So now, what are the things we need to do to set this up? Now, when we can use when we have our favorite parameterization, our formula here becomes this equals, first off, we need to look at which direction our normal vector points. So we're told in the problem that n is directed outward from the cylinder. So the normal vector for this surface right here, for z equals 0, that's going to go in the downward direction. And the formula that we have for our favorite parameterization goes along with the upward. So I'm going to write down the formula and I'm going to put a sign in front. So I'm going to leave some space right there for either a plus or a minus. So the way we evaluate this is the double integral over R1 of negative m times the partial of f with respect to x minus n times the partial with respect to y plus p dA. And don't forget what m, n, and p are. Those come from whatever your vector field is. So that's m right there, that's n right there, and that's p right there. All right. So now, this formula always has the z component, or the k component, is pointing up for the normal vector when you're using this formula, because the normal vector here actually is negative f sub x, comma, negative f sub y, comma, 1. There's an understood 1 that this p is being multiplied by. So that means the normal vector is actually pointing up here. But for our surface, this surface equals 0, it tells us that the normal vector is pointing down. So because they point in opposite directions, we just slap a negative sign in front of that. All right, so now we're ready to plug in everything that we have into here and evaluate. So this equals, and we'll address that region as well. So negative double integral over R1. So we take m that we have from our vector field and we substitute our parameterization in there. So our parameterization, x is x and y is y. So our m still just remains sine of x squared plus y squared. So this is negative sine of x squared plus y squared, and then times the partial of f with respect to x. This is f, its partial with respect to x is 0, so this is times 0. And then minus n. Our n came from our vector field, was y times sine of x squared plus y squared. We plug in our parameterization, but in our parameterization, x is x and y is y, and there are no z's in there, so nothing changes in there. So that's minus y times sine of x squared plus y squared, and then times the partial of f with respect to y, which the partial of this with respect to y is just 0. So times 0. And then lastly, plus we take p and we substitute our parameterization into whatever p is. Our p, though, in our vector field is just 0. So it just ends up being plus 0 dA. And as we can see, all of this is 0. So we don't need to deal with our bounds at all. We're just going to get 0 here. All right, so the surface integral over S1 is 0. So it's not going to contribute anything to our answer at all. All right, now let's address S2. And then we'll do S3, which is actually the side of the cylinder. So S2, our parameterization, is in S2. I already solved for z for us, which means we can use our favorite parameterization. So this setup is going to be very similar to what we just had. and looks like it's going to be identical to what we just had actually. So x equals x, y equals y, z equals 1. And I won't go through this one just because, as we can see, 1, we have our favorite parameterization, which says we're going to use this formula. The region is exactly the same for R1 and R2. So, for S1 and S2, that region R1 is the same as R2. Then our M, of course, is going to be the exact same. Our N is going to be the exact same. Our P is going to be the exact same because those don't have, we would substitute our parameterization in there into M, N, and P. But the M, N, and P in our problem only have X's and Y's in there. So that didn't change. Z is what changed from up here, but there are no Z's anywhere in our vector field. So that means nothing in here at all is going to change, with the exception of possibly our partial derivatives. But our partial with respect to X of this F is also 0. Our partial with respect to Y of this F is also 0. So this integral actually is going to be identical to that integral right there, with the exception of we would have a plus sign in the front because the normal vector on this one is going to point up, but it doesn't matter. Positive 0, negative 0, they both give you 0. So this integral here for this part is going to be identical to that thing. We're going to get 0 for that as well. So the surface integral over S2 of f dot n ds is also 0. So now our work is mainly going to lie in S3. And this will be the first problem that we've seen where for S3, we will not be able to use this formula. Now, for a lot of the problems in your textbook, you can use that, but we can't use our favorite parameterization. So be careful not to have the impression that this is the surface integral formula. That's the surface integral formula of a vector field only when you can use your favorite parameterization. Otherwise, that does not work. All right, so now S3. We need to parameterize S3, which was, what was S3? Was the cylinder. So here, the natural thing. So let me just write down what it was again before I parameterize it. Parameterize it. You know what I'm trying to say. All right, so that was the cylinder that we were looking at, and we were given a Z. It was between 0 and 1. All right, so now we can't solve this for X because we're going to get a plus or minus. We can't solve for Y because we're going to get a plus or minus, and there are no Z's in here. So our only choice now was not to use our favorite parameterization. So we'll use cylindrical coordinates to parameterize this instead of trying to use a favorite parameterization because it won't work here. So here, the natural thing to do is to parameterize this with X equals. Now, keep in mind, you are on the surface of the cylinder. So you don't want to use X equals R cosine theta. Your radius should remain at the square root of pi over 2 at all times. So the square root of pi over 2 cosine theta, and then y equals the square root of pi over 2 sine theta, and then z is just going to be z. And another clue to the reason why you should not use an r here or an r there is because, remember, in your parameterization for a surface, you should only have 2 parameters. If you have an r here, a theta here, and a z there, then you're in trouble because you have 3 parameters. Our parameters are theta and z. So we have the full cylinder. So theta is going to vary between 0 and 2 pi, and then z is going to go between 0 and 1, and that'll give us our cylinder. So now this, in this scenario, our surface integral over S3 of f dot n ds equals the double integral over R3. So now I'm just going to write down the formula that we originally had of the vector field F evaluated at, for us, our R is a function of theta and z. So R of theta z. And then we need to take that and we need to dot it with r sub theta cross r sub z. And then we'll evaluate that double integral. All right, so for our favorite parameterization, all of this is done for us. The cross product is done for us. The only thing that's not done for us is substituting in our parameterization, but the dot product is done for us. Everything that we need is already done for us when we're using our favorite parameterization. Now we just have to start from basic principles and do it ourselves. So first, let's find r sub theta and r sub z, and then find that cross product. So our r is given by the parameterization that we have here. So r sub theta. Oh, and another thing too, I need to look at, once we do this cross product, I need to look and see in which direction does my normal vector point. So it's actually going to be plus or minus. Let's squeeze that in there. After we do this, we're going to check and see which direction our normal vector, this normal vector points. Does it point into the cylinder or out of the cylinder? If it points into the cylinder, we need to use the negative. If it points out of the cylinder, because the problem said it should point out, then we can stick with the positive. So r sub theta. So our partial of r with respect to theta is negative square root of pi over 2 times sine of theta, and then square root of pi over 2 times cosine of theta, and then 0. Our partial of r with respect to z is equal to 0, and then 0, and then 1. And now let's take our cross product, r sub theta cross r sub z. And say, for instance, I do my cross product this way and I end up with my normal vector pointing the wrong way. If you happen to do yours the other way, then you wouldn't need to do anything. So just make sure that whatever you do here, you choose your plus or minus based upon however you opted to do this, because there's nothing to prevent you from doing r sub z cross r sub theta. I just chose to do r sub theta cross r sub z, but it doesn't matter. So now let's doing this cross product. So here we have square root of pi over 2 times cosine theta. Square root of pi over 2 times cosine theta. And then we are going to have negative. So we're going to have square root of pi over 2 times sine theta. And then lastly, we will have 0. All right, so there's our cross products. Now we're going to take our parameterization, substitute it into our vector field, and we're going to dot that with this, and then we'll be ready to evaluate our integral. And we're just going to pay attention. I'll go back and check at the end whether we need to use the plus or the minus on our integral, and then put that on there. All right, so now let's put together f of r of theta z. So our vector field was the I component, or our m as we call it, is sine of x squared plus y squared. So it's going to be for us sine of x squared plus y squared. So here, when we do that, we would get pi over 2 times cosine squared theta plus pi over 2 times sine squared theta, which is just pi over 2. So our first component is just going to be sine of pi over 2. And then our next component was y times, so y times sine of x squared plus y squared. And we already established sine of x squared plus y squared is just sine of pi over 2. And then y is going to be this. So we're going to get square root of pi over 2 sine theta times sine of pi over 2. So square root of pi over 2, what did I say, times sine theta times sine of pi over 2. Then our last component for our vector field, f, was just was just 0, excuse me. So we can't plug, of course, anything into there. But if there were some x, y's, or z's in there, we would substitute that stuff in for them. So now we just have comma 0. And now what we're going to do is we're going to do this dotted with this, and that's going to make up our integrand. And then we have our bounds for our integral are right here. This theta is going to vary between 0 and 2 pi. Z is going to vary between 0 and 1. So now we have the integral from 0 to 2 pi and 0 to 1. All right, so now we have sine of pi over 2 times square root of pi over 2 times cosine theta plus, and we're going to multiply these two, which will just give us pi over 2 sine squared theta times sine of pi over 2, and then plus 0. So that gives us, with these two, we get root 2 over 2 times pi. So root 2 over 2 times the square root of pi over 2 times cosine of theta, and then plus, we multiply these two, we get pi over 2 sine squared of theta. Oops, I forgot about my root 2 over 2. So I put it back here, times root 2 over 2. And these are z's, so dz. And these are theta, d theta. All right, and then we would evaluate that. Now, had we not gotten 0 for our first two integrals, we would evaluate this and add it to both of those. But we got 0 for those, so there's nothing that we need to add this to. But the only thing remains is to check and see, do we need to put a negative sign or a positive sign in the front of this? And the way we check that is by taking a point and plugging it in to our normal vector and saying that this normal vector point into the cylinder or if it points out of the cylinder. And you just choose a point so that to make your life easy. So, and actually I'm going to sketch this, although it's not necessary, but I just want us to be sure we understand what's happening here. So I'm not sketching this yet. I am just sketching us looking at the cylinder from above. If we were to look at that cylinder from above, or look at a trace of that cylinder, say in the XY plane, cylinder would look like this. Now what we're doing is you would have to pick a point on your cylinder. So you can't just pick any old point and try to plug it in here and say I decide to, well, then we don't have any z's in here, so that doesn't help. Usually you would have thetas and z's in there, whatever both of your parameters are. But say I had thetas and z's in there and I picked z equals whatever, 15. Now on the cylinder it wouldn't matter, but z equals 15 was not in our bounds, so I couldn't use that. I should not be using that. You should have to use something that's within here. So when you pick a point, you have to pick a theta in there, comma, a z that's in here. So make sure whatever point you select to your test point, it abides by whatever your bounds are, because that ensures you're actually on your cylinder. So if, for instance, there was some way I could pick a point right there and say I tried to plug that in. I mean, I can in this scenario, but if I did, that wouldn't be on the cylinder. So I shouldn't be plugging that in here to try to figure out any information about the normal vector. It has to be something that's actually on your cylinder. So here, to make my life easy, I'm just going to pick theta equals 0 and see what happens. So if I plug in theta equals 0, that's where I would be if I were to look at the cylinder from above, as I would be right there. I actually should have drawn this with no coordinate axes so we can actually see things better. So theta equals 0. I'm choosing that point right there. So when I plug theta equals 0 in here, I get square root of pi over 2, and then I get 0, 0. So I get the vector that points in this direction and has a magnitude of square root of pi over 2. So I get an outward pointing vector, which means that this normal vector is in alignment with what we were told in the problem, outward pointing from the cylinder. So, I mean, I don't need to write it there, but we would have a plus sign there. If you had done your cross product r sub z cross r sub theta, you would have gotten instead that normal vector would have pointed in. You say for instance, you might have chosen to do, instead of 0, chosen to do pi. If you chose to do pi, you were right there. And had you done your cross product the other way, your normal vector would have pointed that way. And then that would have told you you should put a negative sign right there. But we didn't do that in this scenario. All right, so that concludes section 15.6, and then we'll start section 15.7 in our next video. And we're going to pretend that I was paying closer attention, and I'm going to fix these sine of pi over 2s that I looked at sine of pi over 4 by doing this. There you go. All right, so now we'll act like I didn't compute sine of pi over 4, and I actually computed sine of pi over 2. So I just turned all those to 1s because for some reason when I did all the sine of pi over 2s, I was thinking sine of pi over 4 in my head, or I gave you the value for sine of pi over 4, whatever. But to change those to 1s, I just multiplied by the reciprocal to get rid of that incorrect part that I had in there. All right.